the first reaction with CYP450 that we're going to be discussing is hydroxylation. So we're going to start off with the mechanism. You have R, which is generally speaking, it's generally going to be a carbon or a nitrogen attached to a hydrogen. You're going to break up this bond homolytically. What I mean by homolytically is a bond consists of 2 electrons. You're going to split it right down the middle. Hydrogen takes away an electron. The R atom takes up an electron, and you have 2 radicals generated. This is different than your typical acidity breaking of a bond. With the acidity breaking of a bond, the R takes away both electrons, and then the H plus just goes away. So what we want to look at is how strong of a bond do you have? Okay, is it strong? Is it weak? If it's strong and has a high bond energy, it's going to be tough to form the radical, and it's not going to be as good for hydroxylation. The weaker your bond is, the lower the bond energy is, the easier it is to break it up, and the easier it is to break it up, the more likely you are to generate this key radical intermediate. From there, we're going to deal with the oxine atom. Oxine atom only has 6 electrons. It's electron deficient, so it's going to see, hey, I have an electron on the radical H, I have an electron on the radical R. You're going to combine them together, and boom, we got our ROH atom, or we have our ROH, our hydroxylated R atom. So when it comes to picking where we're going to hydroxylate, a few things that are good. Increasing the amount of substitution around that given carbon. So tertiary tends to be better than secondary, which is better than primary. The reason for that is the substitution helps stabilize the radical intermediate via donating electrons inductively. Okay, of course, it can be bad if the substituents are too big, okay, because if they're too big, what happens is you have steric hindrance, and then you can't put the substrate inside the CYP450 enzyme. Second thing that tends to be good, adjacent double bonds. So if you have a benzene ring attached, that's really good. That's better than having a double bond attached. Adjacent double bonds and triple bonds, those tend to be good because you can donate electron density, or you can donate electrons via resonance by pushing the electrons and stabilizing the radical. Okay, so benzylic tends to be the best, followed by the double bond. Double bond and a triple bond, they're about the same. Double bond is slightly better. The difference is probably I think it's only like 1 kcal. And then the last thing that tends to be good is adjacent electron donor atoms. Okay, I see this with oxygen. I see this with nitrogen. I think of an adjacent oxygen or an adjacent nitrogen as being an activator of a carbon for hydroxylation. And the reason behind that, as we can see, I already drew the resonance structures. You can donate the electrons from the oxygen or donate the electrons from the nitrogen to help stabilize the radical. From here, you're going to have a positive nitrogen or a positive oxygen. The nitrogen prefers to be positive. Okay, the nitrogen prefers to be positive. Since the nitrogen prefers to be positive, N tends to be better than O in terms of activating a carbon for hydroxylation. So now, which position? Okay, general rule of thumb is you want to aim for omega minus 1. Okay, the reason why omega minus 1 tends to be good for alkyl chains is that it's secondary. It's a secondary carbon, okay, and it's towards the end of the chain. Since it's towards the end of the chain, you're not really going to have too much in terms of steric hindrance, and the omega minus 1 gives you the whole secondary carbon. Okay, of course, this is just a general rule of thumb. You should keep in mind substitution, adjacent double bonds, and whether or not you have an adjacent nitrogen or an oxygen. Okay. Now, the other time when omega minus 1 doesn't really work that well is when you have a nitrogen attached and you're looking at like a methyl group versus an ethyl group. Okay, we have an omega minus 1, we have an omega, and we have an omega carbon. You're going to pick the methyl carbon. Okay, you're going to pick the methyl carbon that's at the omega position. The reason behind that is being next to the nitrogen is enough to lower the bond energy of the CH in the methyl group. So basically omega and omegas minus 1, they're both low enough to be broken. So we're not going to be looking so much at bond energy, but in this case, we're going to be looking at sterics, okay? Because CYP450 is an enzyme. You need the substrate to bind into the enzyme. And what's going to happen here is because of sterics, when you have nitrogen with alkyl chains attached, you go with methyl, which would be greater than ethyl, and that would be greater than like your typical longer chains. Okay, so there we have it. That's how the hydroxylation works, and a couple of the reaction determinants that determine whether or not you're going to hydroxylate which carbon or which nitrogen or whatever atom in your given molecule.